Hi everyone, this is another one in the homework help series, and this particular question is, just let me write it down, it's asking us to find the integral of x multiplied by sec x multiplied by tan x dx. So this looks like a bit of a beast. Now, we might just do a little bit of algebra on this to make it look slightly better before we go too far. So let's see how we go. We've got sec is 1 over cosine, and tan is the sine of x over the cosine of x dx. So this is sine of x over cosine squared x dx. Now if we can integrate that, that's the same as what we started with. So I'll begin by thinking integration by parts, and let's identify what we're dealing with here. X is an algebraic term, and the sine of x over the cosine squared of x are trigonometric functions. So it looks like I'm going to have u is my algebraic term and dv is going to be my trigonometric terms. So let's set that up. Let u equal x, and we'll have dv equals the sine of x over cosine squared x dx. Now the usual process here is to take a derivative. Du dx would equal 1, and so that gives us a very nice simple relationship that du equals dx. Over here, to find v, we will need to integrate sine of x over cosine squared x dx. Now that's not going to be a simple one. We're going to have to use a substitution. I note that the derivative of cosine is negative sine. So I could write this as the integral of, well actually let me go off to the side slightly for a minute. I'll define this, I will make my substitution. I won't use u or v, I've already used those letters. So I'll say let q equal the cosine of x. Let's take a derivative. dq dx equals negative sine of x. So dq over, now it'll be the negative of dq over sine x should equal dx. Now I'm good to substitute. So I have sine of x in the numerator. I will write this as q squared instead of cosine squared, and dx now becomes negative dq over the sine of x. So we can cancel the term sine, the sine of x there, and we end up with negative integral of q to the power negative 2 dq. That's quite doable. So to increase the power from negative 2 would become negative 1 and divide by the new power. So this is literally q to the negative 1, and q, remember, was cosine of x. So it is cosine of x. Now I'm going to be very careful how I write this power of minus 1 so it doesn't look like an inverse trigonometric function, and that of course is the secant of x. So that was slightly more involved than perhaps we would normally have, but we're now ready to apply our integration by parts formula to what we originally had there. So let's do that. So integration by parts, the integral of u dv equals u multiplied by v, subtract the integral of v du. So if we just run back to the top, remember u was x and dv was this sine over cos squared, but that's equivalent to sec x by tan x. So it's really what we're talking about here. X sec x tan x dx. And I'll write it like that because that's the way that the question was posed. Tan x dx. Now this is where we have to do our working. So u equaled x. V is sec x minus the integral of sec x, and remember du equaled dx. So this is good, but we now get to a point where we have to find the integral of sec x, and that's not a trivial process. So I'm going to call that equation 1, and we'll come back to that, and when we do come back to that, we'll just have us go off to the side here, and we'll find what the integral of sec x dx is. Now, we know that sec is 1 over cosine. Now, it doesn't look obvious that we could use substitution or any other familiar method. So here's a bit of a trick. Let's multiply the numerator by cosine x, and let's multiply the denominator by cosine of x. And you might wonder why I thought that was a good idea. Well, hopefully you'll see in a moment. I'm now going to use the Pythagorean theorem to write 1 minus the sine squared of x dx. And that's starting to give me the possibility here of doing a substitution, because the derivative of sine is cosine. So I could let, what's a pronumeral I haven't used? Let's go with r. Let r equal the sine of x. So dr dx equals the cosine of x. dr over the cosine of x would equal dx. Let's make this substitution. So I still have cosine of x in the numerator, and it's now 1 minus r squared in the denominator, and I'll substitute for dx. This is dr over the cosine of x. So that conveniently cancels, and I have an integral of 1 over 1 minus r squared dr. And that's also not an obvious one, because this one we don't have a it's not like it's an inverse trig function. If it had been 1 plus r squared, we would have been happier, because that's one of our rules, but we can't just magically change a minus r squared to a plus r squared, because it would make our life easier. So I think what we're going to have to do with this one is another aside. And we're going to have to use partial fractions to decompose this expression. This is a second degree polynomial in the denominator, and it's a constant term in the numerator. We should be able to decompose this into partial fractions. So let's go. We have 1 over, and it's 1 minus r squared. Well, I can see that that's a difference of squares. This would be 1 plus r, 1 minus r. And there's my two factors. So I'll have 1 plus r as the denominator of my first partial fraction, and I'll have 1 minus r as the denominator of my second partial fraction. Now, writing this together, so I have now a common denominator. I would have a multiplied by 1 minus r added to b multiplied by 1 plus r. So multiplying and collecting like terms in the numerator, I would have a plus b as the two constants, and then I would have, what would I have? I would have b subtract a multiplied by r. Now, we can see from the term up here that this is really 1 plus 0 r. We could consider that to be, it looks like the word or, doesn't it? Let's make that a bit larger so it looks like an actual 0. 1 plus 0 multiplied by r. So I can make the connection here between the constant 1 and the term a plus b, and the constant or the coefficient 0 and b minus a. So let's just solve those. A plus b equals 1. I might write negative a plus b equals 0 to make it convenient. Adding these expressions, I would have 2b equals 1. Well, that implies that b equals 1/2, and if b equals 1/2, then looking here, a plus b equals 1 also implies that a equals 1/2. So I could go back here now and I could rewrite this integral as 1/2 over 1 plus r plus 1/2 over 1 minus r. So let's go back and pick it up from point 2 where we left off. So I'll just recopy what I had there. Integral of 1 over 1 minus r squared dr. And we can see from our work on partial fractions that that's 1/2 over 1 plus r added to 1/2 over 1 minus r. Now, integrating each of these, I would have 1/2 multiplied by the natural log of 1 plus r. Then I would have 1/2 multiplied by the natural log of 1 minus r. Now remember, because we have to think about the derivative of this little expression, derivative of 1 minus r is -1, so when dividing by -1 it really just becomes a negative there. So let's take the factor of half from some brackets, and I would have ln of 1 plus r minus the ln of 1 minus r, and that I think is best as the natural log of 1 plus r over 1 minus r. Let's just pause there for a sec. So, sorry about that, just had a little pause there. Now, where were we up to? We were finding the integral, weren't we? So this is the integral of this expression, and of course that's just part of what we were doing, because r was a substitution from way back there. R was actually sine of x, wasn't it? So if I were to pick up from there, then let's go even further back. I've lost my train of thought completely. Sorry about this, folks. So this was to calculate the integral of sec x back there at that aside, wasn't it? And that was point 2. So we're picking up from 2 here. And it was the integral of sec x dx. Now we've determined that to be 1/2 natural logarithm. I probably should have had some absolute value signs there. 1 plus the sine of x over 1 minus the sine of x, plus an arbitrary constant of integration, of course. Now that completes the aside that the first aside that we were doing was to find the integral of sec x. So now we can go all the way back here from point number 1, which is the question we were originally doing. Integral of x sec x tan x dx. So here we go. This is picking up from where we left it off at point 1, the integral of x sec x tan x dx equals, now let's go all the way back to where we were, it equals x multiplied by secant x, and then subtract this integral that we just solved. So x sec x and what we just solved is staring right at us here. It is 1/2 by the natural log of 1 plus the sine of x over 1 minus the sine of x plus a constant of integration. Now, in my opinion, that would be a reasonable place to finish, but that doesn't quite match what's written in the answers at the back of the textbook. So now it just becomes a matter of using a little bit of algebraic manipulation until we get something that looks the same as what's in the textbook. Now, I'm going to employ a little algebraic trick here. We have 1 plus the sine of x over 1 minus the sine of x. What if I multiply both top and bottom by 1 plus sine of x? And again, you'll probably wonder, why on earth would we do such a thing? It'll become clear in a moment. Now I'm not writing, well, I'll write the half, I'll put the half there, but just be prepared for things to change in a moment. So the numerator here is 1 plus the sine of x squared. The denominator is a difference of 2 squares. It's really 1 minus sine squared x. But wait a minute, that's cosine squared x. Now can you see what I'm going to do with the power half? Sorry, I'll leave the negative sign where it was. I am going to put all of this in brackets and raise to the power of half. That looks like a good idea, because the numerator is a squared term and the denominator is a squared term. So we have, what do we have? We have the natural logarithm of 1 plus sine x divided by cosine x, no longer squareds, plus our constant. This is x sec x minus the natural log. Well, 1 divided by cosine is sec, and sine divided by cosine is tan. And that's where we're going to stop, because now that matches the way the answer is presented in the back of the textbook. This has been quite a good question. Thank you for asking. And it's when we scroll back, we can see, well, lots of different techniques have been used there. Integration by parts to begin with, a little bit of lovely algebraic manipulation here. Then we had a substitution method. Further down here, we came across an integration with partial fractions. So this is a great question. It sort of ticks all the boxes for all the different techniques we've used. Thanks for watching.